blank direction.
I had expectations. That's what it said.
Oh.
What was the question?
Yeah, bro.
Well, you can do the second one.
11 yes.
Okay, can you move on?
Sure.
Thank you.
Yeah.
Sorry, it's not like great coding. When it says there's B to pass, that's pass with a D or a C or both?
I'm counting C as pass because that's
Okay.
transferable.
Just making sure.
Yeah. I mean, technically D is pass, but we all want to transfer the stuff possibly. Yeah, so that's to make a C. Cool. Yeah.
What's the best grade you can get without ever doing homework?
Well, let's see.
Isn't it on there?
93?
If you got 100 on everything, homework actually ends up counting at roughly 5% because it's averaged together with the quizzes. So if I take homework out by itself,
95?
exactly.
That's your biggest secret.
Sure. I
I
mean,
would have known that.
I would love to make homework worth nothing. Because if you don't do the homework, you're already screwing yourself over. So technically, why should I double hurt you? Right? But if I make it worth nothing, nobody does it. I know because I've tried. And I don't blame you. What do? I got all this shit to do. Which one do I actually have to turn in? This. All right, statistics. So I understand that. So I've got to make it worth something.
Yeah.
And you just shined a light on, oh, it's not worth that much.
Sorry.
Well,
it does if you have like 88 trying to get an A.
But at the same time, I
It
do
does.
want to make it known that it's not worth cheating on. Shit, if you make A's on the homework because you cheated and you get it past me, yay for you. You haven't done enough practice to pass the damn test.
Right.
So you got 100 on 5% of your overall grade. Ooh, way to go. Do you see what I'm saying? So I don't want it to count too much and I don't want it to count too little. Yeah.
The amount of work you had to put into just straight up cheated.
I know. In general, that's true. If you're that creative and that hardworking, and something beyond cheating, it'd be amazing. Okay. So just to remind you guys last time what we were talking about, and today we're actually going to look at a concrete example of this thing I was talking about last time. Last time I went back to one of my favorite little examples about ages in Florida. And remember, what was the most likely thing? This is taking one person at a time. So, in general, we don't do this in statistics. This is really good when I want to compare, if I pick one person, what's the probability of this or this? I want to compare it to a distribution of single people, one at a time. But what do we normally do? We take groups of 20, 80, 1,000. So I can't use this picture. I need to use a picture that represents groups of people. How would they be distributed? They're not going to be distributed like this. Because any group I pick, what's the most likely average for that group? The real average, right? Right now, how many individuals are on top of that real average? Actually have the real average age? Nobody. But the minute I take groups, I don't even care if I take just groups of 2. This is going to grow a lot. Obviously, nothing right now. But it's going to be the tallest now. Any group of people I pick, what's the best guess for their average age? The average of the whole population, right? So what happened last time we looked at, if I took 20 people at a time, the most likely thing to happen would be a mixture of the 2. So I get this peak in the middle. I probably still have 2 little peaks on the sides corresponding to those peaks. The neat thing about this section is it says the more you take in your sample, the larger the sample size, the more normal your distribution gets. And this is officially called, you're going to love this. This is called the sampling distribution of the sample means. And again, that's really trying to hammer home the idea that here I'm graphing individual ages. Here I'm graphing groups of people's average ages, right? That's why it's a distribution of sample means. Not individual ages, but group ages. How are we doing so far? And so that by itself, I'm hoping, is kind of nice. It kind of makes sense, hopefully, right? So if the average age in here was 26 and I randomly select 5 people, what's your best guess for what their average age is going to be? 26, because we intuitively understand that their average should tend towards the real average. Okay, I'm hopeful. There is a chance I could randomly pick a lot of young people or randomly pick a lot of old people. How often is that going to happen? Not nearly as often as a mixture of people. So the ideas behind this are actually semi-simple. They kind of make sense. They actually jive with what we do in real life. The math associated with this is also simple, but the math associated with trying to show this gets a little gross. That's why I wanted to step you through it with an example. So here's my example. It's probably the most colorful handout I'll ever do.
One person at a time.
Huh?
Yeah, that's what you'll get. You select one person at a time. Like NCX. You choose one. If you only choose one, that's what it's going to happen. It's pull them up.
So like multiple sections of each class or.
Yeah, it is colorful.
See? You took it. Oh, I haven't got it.
Someone spent that some dollar
They should have put it in my mailbox. I just haven't been in my mailbox.
We'll have to pay for ink for the Quick numbers, 1, 2, 3, 4. Yada yada yada. Verify that me and yours. Times P.
All right, guys. So, on first glance, this is a very busy handout. There's a lot of stuff going on here. So, you're going to have to do this process for section 6.4. So I wanted to give you this handout to show you the work. I mean, there are examples in the book, but they do skip a couple steps or don't explain themselves in a couple areas. So I wanted to give you this handout to help out. It's my hope. So here's the idea. If I put 4 numbers in a hat, so let's say numbers 1, 2, 3, 4. This whole process really doesn't matter what numbers I pick. I could pick almost anything. Of course, the probability I pick any of them is 1/4. They're all equally likely. Right? Put them in there, shake them up. Which one I'm going to bring out was each one has a 1 out of 4 chance. How are we doing so far? So the histogram is going to be pretty damn boring. 1 has a probability of 0.25, 2, 0.25, 3. It's what we call a uniform distribution. Right? So if you're getting into Chapter 6 homework, that should sound familiar. Uniform distribution. Because it's uniformly distributed. If I were to do the x p of x stuff, and I didn't do the work up here, but if you were to do, remember, make x p of x L3, L4, x squared p of x, and do all the formulas, you should get this mean and this standard deviation. You with me so far? So I expect to get a 2.5. Now, if I put my hand in there, am I going to get a 2.5? So what this really means is if I do this many, many times and average what I get, I'd expect that average to be close to 2.5. This is related to that question, is it wrong to say an average of 2.5 girls out of 5 kids? It's not wrong. That's not trying to say there's half a kid running around somewhere, right? Just the legs. That's a little freaky. But all it is averages don't have to come out to be whole numbers. Because if I have 10 kids, I expect to have 5 girls. So 5 kids, it's got to be half of that. It's got to be 2.5 girls that I'd expect. That's just an average. Sometimes I have 3, sometimes I have 2, sometimes I have 1. It all averages out to 2.5. Okay, so far so good, right? Not too bad. So this is old stuff up here. Here comes the new stuff. And this is what I really want you guys to understand. My data up here. How big is my data set up here? How big is my sample space? How big is my collection of data?
16.
Think physically, what do I have in my hands? What am I doing? How many options are there? 4. My data set is 4 big. 1, 2, 3, 4. You with me? If I start taking samples of size 2, now what the hell does that mean? I reach in, I pick up a number, and then I put it back in, and then I pick another number, or I reshuffle it. So it's possible I can pick the same number. You with me so far? This is with replacement, right? So I pick a number, put it back in, shuffle it, pick another number. So what could I get? I could get a 1 and a 1. And what's the average of that? What's the sample mean? 1. This is a sample of size 2. There's the sample mean. The next sample I could possibly get would be a 1 and then a 2. What's the average? So that's how I created this. You with me? I could get a 2 and a 3. I could get a 3 and a 4, so forth. So that's all the possible sample means. So when I make my picture that represents my groups, that represents individual pieces of paper. I can pick up 1/4 of the time. Here's the cool thing. What was the average up here? 2.5. If I plot these, if I just plot these, what happens the most often? Look at the picture now. The most likely average to get is 2.5. Well, of course it is. It's almost silly if you think about it. Of course it is. That's why we call it the average. That's the expected value. That's what I expect to get. It's nothing amazing, Jeff. All right. The really cool thing about this is, what does it look like? What kind of distribution? It's already looking normal. Of course, it started off, to tell you honestly, it started off pretty nice. Because that is definitely symmetric. Right? So it's got that property already. But what this theorem says, no matter what the original thing looked like, it could be some freaky ass thing, if I take a large enough sample, it will become normal when I plot the sample means. Let me say that again. No matter what the original thing looks like when I plot individual people's ages or whatever, when I plot that, if I take samples and plot those averages, it's going to become more and more normal. The magic number is 30. To get a sample size greater than 30, then any distribution could be, well, will be considered what I call normal enough. Normal enough.
Why the 30? Yeah.
They actually did computer simulations where they took all these different populations, as many different ways to do it as they could imagine, and they had the computer just pick all these different size samples, and they saw most distributions. In fact, basically all of them, almost all. There's a couple really freaky examples I know. Almost all of them around 30 became normal. Some of them became normal after 2 because they started off pretty damn normal to begin with. You with me? And if you start with a normal distribution, you just pick 1. It's already freaking normal, right? But they made some freaky ass shit. And they said, okay, if I take a sample of 30 and plot those averages, it actually became normal, what I call normal enough. What the hell does normal enough mean? Right? This sounds like we're all going to see a psychiatrist. Oh, you're normal enough. What's normal enough mean? Why do I even want this to be normal? What becomes easy if I know it's normal?
You can do championships, or you can do the don't remember what it's called, but it's
Chubby guys.
The other one, Chubby Dude, is good for anything. What's the better one? What's the more
Empirical.
the empirical rule, which is now represented by what? What do we use now instead of memorizing 1, 2, 3? What do we use that's even better? We use the table. You can't use a z-score chart unless you know it's normally distributed. So normal enough means the probabilities on that sheet are close enough. With me? So in statistics, a huge deal in statistics is any case I'm in, what tells me it's normal enough? Because if it's normal enough, my probability questions are easy. Just look the damn things up on the table. You with me? If it's not normal enough, shit, I need stuff from statistics 2. And we're in statistics 1. All right. Statistics 2 is where we go, all right, you learned about normal. Let's talk about when it's not normal. What weird shit do you have to do then? How are we doing so far? I mean, that's okay. Maybe. So in order to use a z-score chart, I have to tell you it's normal. If I don't tell you it's normal, technically you can say, you didn't tell me it's normal, Jeff, I can't do shit. And I'm waiting for the day that somebody's actually got the balls to do that. Right? But if I tell you here, I took a sample of 38 whatevers. I don't care if I don't say it's normal, bam! It's normal enough. Then you can't say that because then you get it wrong. You're wrong. It's more than 30. It's normal enough. How we doing? Okay, cool. Okay. So here's some more straight up math. And here's actually the only thing that changes. Notice that the average of this is still the average of the old one. Right? The average doesn't change. What changes is everything kind of moves to the middle. You with me? And you see that with this example up here. Everything kind of moved to the middle. So what actually gets smaller? Everything gets closer to the mean. Standard deviation gets smaller. And actually, here's the formula for what the standard deviation does. Here's what the standard deviation used to be for up here. Here's what the standard deviation was for individuals. The standard deviation for groups of size 2 is the old one divided by square root of n. So if you take the old standard deviation divided by square root of 2, you get this, which is exactly what the standard deviation is. If you actually did the whole x squared p of x stuff, you would get this. That is so freaking cool. So if you took a sample of size 3, could you figure out what the standard deviation would now be? You would take 1.118 divided by square root of 3. Maybe. All right. So you desperately, trust me on this, want to keep this next to you when you're doing your section 6.4 homework. Which always some people just kind of skip it. They look at it and they go, I'll just forget about that. But try it out. They only signed, I think, like 4 problems or something. So here's the nuts and bolts. Let's do a couple of examples that actually show you how does a problem change with this stuff. I love purple. Let's say one of my favorite examples for some reason. Right here. Where's the stuff? Makes you high if you're not careful. Did you ready for your stats? Oh, makes sense now. One of my favorite examples was from a previous edition of the book. It said kindergartners. I think that's roughly how to spell it. Have a mean height of 48 inches. Yeah, exactly. With a standard deviation of 1.3 inches. Now here I'm going to tell you it's normally distributed because I have a specific thing I want to show you. So they're known to be normal. Cool. All right. And to tell you honestly, whenever you see something said known to be normal, they actually are saying known to be normal enough. They're not perfectly normal. They're normal enough. Here's question 1. If we pick one kid at random, what's the probability that the kid is, let's do this, in between 45 and 50 inches tall? That is an old problem. Do it. There's nothing new there at all. It's a straight up normal z-score, look up the probability problem. Let me just interrupt for a second. What kind of work are you guys doing? What are you doing to these numbers here?
Subtraction.
Okay. Subtracting what now? Be careful. So you first find. Okay, so we can do 50 first. So 50 minus what to get the z-score? 48. So it's got to be minus the mean, right? How many z-scores do I have to calculate here? 2. One there, one there. I've got to turn each data point into its own z-score. 50 minus 48 divided by 1.3. And whatever the hell that is. It sounds like 1 point something. And 1.54. That's what you guys got? 1.54?
Yeah.
Now let me just stop right there. Do you guys see why I did that? I can't get the probability unless I use the z-score chart, and of course the z-score chart needs z-scores. Gotta make sense. So I've always got to turn any data points I'm interested in, I've got to turn them into z-scores so I can look up their probabilities. And I desperately, now, it's really easy as a student to lose the connection between finding z-score, look it up, and then forgetting why that works. The further I get away from the mean, the more area there should be in there, right? So that chart is just a representation of how z-score getting bigger means more area below it. You can see that happening. So that chart just shows you how much it changes as you move around. So here I am at 1.54 up here. What is the z-score for 45?
Negative 2.13.
2.13?
2.31.
3.1?
Yeah.
Okay. So now if you look up, now be careful. Do not subtract z-scores, because then you move where you are. These show you where you are. You look up the areas. Look up the areas and find out what they are. So what is 1.54? It's hillbilly statistics.
0.9382.
9382?
Yeah.
Everybody see that? When you look it up in the chart, if you've missed some recent class, you are probably really lost. You should probably come see me. What about negative 2.31?
0.0104.
0.104? And how do I get the area that I want? Subtract those. Right? So it looks like you get 0.92878. There's an 8 in there somewhere. We subtract those, right? Is that cool? So it only makes sense if there's this much below that. If I subtract this much off, I'm left with what's right in the middle. That makes awesome physical, visual sense. So what does that mean? What does that number that I just found actually mean?
That's the probability that the kid will lie.
Beautiful. So one way to say it is it's the probability that that one kid will be between 45 and 50 inches tall. Another way to say it is 92.8% roughly of all kindergartners are between 45 and 50 inches tall. Those are two different ways to say what we just found. And you could damn well expect me to say, explain what you just found. That will be a question several times on the test. Yay. So, what about the new stuff? How does that look? Alright. So here's the trick. Here's the thing about when to know to change the standard deviation. If I take a sample, obviously, because I need an n for that equation, right? If I take a sample and ask you about the sample mean, it sounds like a note. If a sample is taken, and they ask you about the sample mean, then you know to do this. Then I've got to do this. Just realized. Yay! So if sample's taken and they ask you about the sample mean, so what would that look like? They would say this. We randomly select 17 kids. What is the probability that their average height is between 45 and 50 inches? Now, even before we do this problem, what's the main idea behind what changes when I take samples? What really changes with my picture? What's the main thing that really changes?
Standard deviation.
Standard deviation gets smaller. I would have also accepted it starts to look more normal. But I was looking for the standard deviation gets smaller. Everything gets closer to the mean. So this was 90, almost 93%, was around the mean. That number should then be higher. Because now I'm taking samples, everything should get closer to the middle. Everything should kind of move in closer. My standard deviation is small, everything should get moved in closer. So let's try this workout. So here, we took 70 kids, took a sample, check. They asked me about the sample mean. Check. Therefore, I know I must change the standard deviation first. The funny thing is, all my work is the same after that. I just don't divide by 1.3. I divide by the new standard deviation. So here we go. Here's how the work would look. What's the new standard deviation going to be? It's the old one divided by the square root of n. What was the old standard deviation for individual kids? 1.3. I can't use that one directly because now I've got groups of 17 kids. I need the standard deviation for groups of 17. So divide that by square root of 17. .3 something.
0.315.
And now the whole thing's the same. You got the same picture, really. There's your 40, what was it, 48, 45, 50. I still want the area in the middle there. I still make my z-scores, but now I'm going to do 45 minus 48 divided by 0.315. And you'll see something interesting. You get like 9.
Negative 9.52.
Negative 9.52? Is that what you guys are getting? All right. So that's negative 9.52. And up here, what's Z50 become? Z for 50. Like 6 point. I think. Yeah. 6.4. What is it? 6.35. That's pretty close. All right, 6.35. Now, real quick, I want to ask you before we figure out how the hell to look those up, because are those on the z-score chart? No. Let me really make sure you understand the idea here. If I went out and I saw one woman walking down the sidewalk that was 7 feet tall, that would be like, whoa, right? If I saw 20 women whose average height was 7 foot tall, wouldn't that be a lot more of a whoa, right? Like a, what the hell? Is there a convention? Is there a meeting for women that have to duck going through doors? I don't know. You with me? I'm not picking on tall women. It's just a good visual. You with me? That's what we're finding out here. If I take a group of 17 kindergartners, they are not going to have an average height of 45. They're going to be much closer to the real average height. You with me? That's why this is now technically so damn far away. Because they should be a lot closer to 48. So now let me see if you guys can understand this. What is below the 45? What's below negative 952? How much do you think is actually out there? It's not on the chart. And that's what the chart says. The chart sucks in that case. Because when I'm out there, about negative 350, I'd say 0.001 is good. If you get to 4, 5, 6, you're basically 0%. So how much do you think is below this one? If I'm way up at 6.35,
Like 1.999.
approximately 100%. So I'd say the answer to this question would be about 100% chance. It is really unlikely that a group of 17 kindergartners would have an average height outside of here. So it's very likely they're going to be inside there. Okay, hopefully. Again, the main thing to get from here is I desperately want you to understand the concept, but the nuts and bolts math is pretty damn simple. When I take a sample and I ask you about the sample mean, I change the standard deviation and then I do all the steps the same, just dividing by the new standard deviation. So the math doesn't change that much. Concept's a little freaky.
It doesn't seem that unlikely. You know, if you think about it, it doesn't seem that unlikely. I mean, I understand it is, but
I got you, but that's because it's really easy to lose sight of the fact that the 17 kids would have to have an average that was so far away from the mean.
yeah.
Right? So that's where it goes counter to our intuition. Okay, that's plenty for today. So I will see you on Thursday.
I made my correction. So that makes sense right now?
Oh, cool. Okay.
So I just want to go through over here. This and less than 8 so I should better go no. So that's going to be add all these up. What's going to be less than 8 hours.
Yep, good. Or you can do 1 minus 39.39. Less than 8's got to be 1 minus 8 or more. Either way.
I did both of them, so I like that correction.
Plus everything is so nice.
So if I took a 1 and a 1 out, what's the average number? 1. If I took a 1 and a 2 out, what's the average? 1 plus 2 is 3 divided by 2 is 1. Cool. So I just average those numbers all the way.
You know what's funny? That test is after spring break.
Yeah, I know. Which is gonna be fun.
Oh, good.
See who remembers.
See me.
Right.
So of course the main thing you can do for yourself is anything you have not corrected. You can see it's not impossible to pass even if you don't correct. But the more things, especially that you corrected him in time for the next steps and turn it in, and you get everything right, that would push us up to that.
Did you got this one over here?
So I can
Right.
film it
There.
all of them?
Oh hell yeah!
The answer is
You won't. The rest of them will be late,
This isn't
except for the quiz 4. That'll be
Yeah.
on time.
Right.
Oh,
I love
dude,
it.
these Z-scores.
And this can go up to
That's
70.
that's how many standard deviations it is away. You remember?
But this is the big one. This would really boost your grade a lot because the tests are, of course,
Do you remember when we
more
had this?
percentage for those. Cool.
Yeah, right.
Sure.
I did math with my place back,
Oh.
and I missed the worksheet.
And then out
Oh,
here,
yeah.
that's like
That's
7%.
And
It's in
sorry
here.
for being late. I was
This,
midterm.
this is what,
no,
4?
that doesn't sound. Let me know
3,
if that
4?
makes sense.
So it says how much is out here? Like almost,
That's the main thing to get off of there. Yes.
almost nothing
Oh,
out
yeah.
there, right? And then this one's 6. So plus 6 standard deviations out here. There's almost nothing out here. Right? So everything in the middle is probably like 100%.
Exactly. Or it's like, it's really like 0.9999996 or something. That's effectively.
What I'm saying is just how did you figure it's 100? That's why it's just confusing.
All right. So if you look up, if you do it by the book, if you look in the chart,
I'm not. I just.
come here. If you look in the chart, negative 952 is lower than that. So they tell you that's officially 0.001. 6.35 is off the chart the other way, and they say 3.5 and up is 0.9999.
I thought they were too, but they're not. It's not like.
Subtracting those, you get 0.9998, which is still almost 100%. That is wrong, though. The book, I hate that they generalize it, because as you go further and further out, this gets lower and lower and lower.
Yeah.
So my picture's a little wrong because I wasn't sure where to put these, but now I know it's actually way the hell out there. It's 6 standard deviations away. So how much is up here? Effectively none. Nothing. Theoretically, yes. Effectively, no. So that's why I don't say 100%. I say approximately 100%. To make sure people don't realize that they do realize it's not a given that this will happen, but it's almost. Right? Sort of like the sun's going to rise tomorrow. Hopefully it's effectively 100%.
Yeah.
Right? Yeah.
Sounds good, thanks.
No problem.
Yeah, that was just 2 days.
So this is not
Math
including
makes me
homework.
hungry.
So you have all the homework turned
I
in.
just want to pass my stupid art.
Oh,
You
okay.
don't still have to make corrections.
Yeah, I just have a
That's
test on
Oh.
Friday.
You have none of them
How do you
turned in
art
at all.
test?
That's
What?
what you do.
Art test?
And
Yeah,
people
I
freak
know
out
it.
that they're like, well, it doesn't go up.
I know,
much,
right?
but it goes up.
Just had a
If you were at 100, it wouldn't go up at all.
Right.
If you're at 50, that's where it would go fully up and down. So, yeah.
But like.
So if you're there, you're good. If you're halfway in between, you're halfway in between.
And
I don't really do the
that
homework till the
can
end.
go up with the test too.
Oh, and this one, of course, is whatever situation you're in. This is what you have to average on test 2, test 3, all the quizzes, and the final
Okay.
to pass. You get a 7.
All right. Cool.
Cool.
So this is one more test of quizzes that'll possibly
Oh, no.
back up.
You got 2 more tests to do, so at least 1 or 2 more quizzes at the least,
Okay.
and then the final.
And we're not doing quiz 6 on Thursday, right? Because I know I was emailing you and you said you might.
Yeah, I don't think I announced we would do a quiz.
I wasn't at the beginning, so I didn't know if you said.
No, I didn't. No.
Perfect.
So we have a
Thank
quiz
you.
on this Thursday.
No.
You might not want me to create.
Oh yeah, because standard deviation has to go out at least 3 places.
Oh, I saw last time you said at least 2 or 3.
No, always
Because I-
at least 3 on standard deviation. Z-scores 2, because the chart only goes out 2 places. But I am very consistent about standard deviation has to be at least 3 places.
Z-score and standard deviation at least 3 decimals.
Well, Z-score 2, because the chart only goes out 2 places.
So standard deviation
At least 3, if not more.
Okay, and this is for.
I didn't take any points off, but it's less than or equal to. Because if something could be 0, that'd be fine. Something could be exactly 1 as long as everything else is 0.
So if it could be equal or not equal.
Yes, good. The lowest can be 0, the highest is 1, so those are inclusive. Cool.
And I don't know, I'm around here A, B, or C or.
Oh, this is everybody. So like there were, on test 1 there were 13 A's, 17 B's, so forth. So on quiz 4, you got an A, and there were 10 A's. Just to let you know.
Yeah.
And this is overall average, so you have a C, there's 6 C's. Yeah.
This is a keep going working, right? Nothing right here represent for right now.
Well, that does represent right now. If right now you have all the homework turned in, that's what you actually have. That's your real average, because I didn't count homework up here. And if you have none of them overturning, that's your real average. This is what you have to average on everything left in those two situations to pass, to get a
So
7.
from now on, I can jump for this number up to pass this class.
Exactly. So you could actually technically fail everything and not do anything. If you make 65.3 on everything left, you will pass. And of course, I hope you want to get more than just. Yeah. But that's some people are at the point where they're like, should I stand and stop? That's why I put that on there.
Yeah. Yeah. Yeah.
There's a crazy kickstand.
I know, I love it. When you're hiking, you can wrap it around a tree limb.
Oh, really?
Yeah.